Here we'll introduce what are called one-sided limits. But first, here's the function 1 over x minus 2 squared. What's the limit as x approaches 2? If you'd like to review vertical limits, like this one, instead, then click down here. Exactly, this limit is positive infinity. If we look at a bar with height n, no matter how high we set the bar, we can always find a narrow enough tube so that the function is always above the bar inside the tube. So this limit is positive infinity. Now let's look at a slightly different function, 1 over x minus 2, this time without squaring the denominator. Which of these is the correct graph for this function? Right, this blue curve is the correct graph. Just like 1 over x minus 2 squared, this function, 1 over x minus 2, has a vertical asymptote at x equals 2, meaning the function gets arbitrarily close to this line. Now what's happening to f of x as you approach x equals 2 from the right side? In other words, if we follow a point on the curve, what's happening to the point's y-coordinate as its x-coordinate approaches 2 from the right side of the asymptote? So it looks like this function is going to positive infinity as you approach x equals 2 from the right. But what's happening to f of x when we approach x equals 2 from the left? So this time we're following a point over here, and we're asking what's happening to the point's y-coordinate as its x-coordinate approaches 2 from the left side of the asymptote. So as we approach x equals 2 from the left side, this function seems to be getting more and more negative, approaching negative infinity. Let's take a careful look at what's going on around x equals 2 with this function. We'll look at the right side first. No matter what bar height n we pick, if we're close enough to x equals 2 on the right side, the function stays above the bar, even if the bar is really, really high. Here's how we can write down the limit of this function, 1 over x minus 2, as x approaches 2 from the right. We've included a tiny plus sign here because we're saying this is the limit as we approach from the positive side, that is, from the right. And because we can find a region to the right of x equals 2 where the function is always above the bar no matter how high the bar is, this limit is equal to positive infinity. Similarly, on the left side, no matter how negative we make the bar, if we're close enough to x equals 2 on the left side, the function stays below this bar, even if the bar is really, really negative. And here's how we'd write down the limit from the left side. This time we've included a tiny minus sign here because we're saying this is the limit as we approach from the negative side, that is, from the left. What would you say this limit is equal to? Positive infinity, 0, or negative infinity? Right, this limit equals negative infinity. Next, let's look at another function, x divided by the absolute value of x. First, which of these is the correct graph for this function? If you'd like to work this out step by step, then just click over here. Exactly, the purple graph is the correct graph for this function. The function equals 1 when x is positive, negative 1 when x is negative, and the function is not defined when x equals 0. So we have hollow circles on the y-axis, which is when x equals 0. So for this function, let's look at the left and right limits around x equals 0. Try evaluating these two limits. What value does f of x approach as x gets really, really close to 0 from the right or positive side? And what value does f of x approach as x gets really, really close to 0 from the left or negative side? Nicely done! At x equals 0 for this function, the right limit equals positive 1 and the left limit equals negative 1. These are the one-sided limits for this function as x approaches 0. So now that we've determined what the right and left limits are at x equals 0, perhaps we can now say for sure what the limit is as x approaches 0. When you don't include a small plus or minus sign in the limit statement here, that means you're talking about the two-sided limit. To evaluate this expression, you're asking what value this function is approaching as x approaches 0, regardless of whether you're approaching from the left side or the right side. But for this function, you get two different values depending on whether you're approaching 0 from the left or from the right. So for this function, this two-sided limit does not exist. Last question. Take a look at a few more functions here. For which of these graphs does the two-sided limit as x approaches 0 exist? In other words, for which of these graphs do the left and right limits around 0 equal each other? Right. For this first function over here, the left limit at x equals 0 seems to be going off to positive infinity, while the right limit equals this y-coordinate down here. So the limit as x equals 0 does not exist for this function. For the second function, the left and right limits both equal the y-coordinate of the hole in the function over here, so this limit exists. And for this last function, the function is going off to negative infinity as x approaches 0 from both the left and right sides. Because the left and right limits both equal negative infinity, the two-sided limit exists and equals negative infinity as well.